So last time we started on this idea of this two-body relaxation. It's an actually extremely important concept that you should all be sort of familiar with, because it's like the foundation of the technical things that you will learn. So last time I had actually mentioned that for a lot of cases, you can actually ignore the fact that galaxies are made of individual stars, and you can use a smooth density distribution. Okay, we actually did this impulse approximation. So let me quickly write down where we were. We considered stars all of mass m, and then we sort of considered this test problem where there is a mass of star. So all stars are of mass m, and we are actually not doing an exact calculation. Okay, so we are sort of doing we are ignoring factors of order 2 in this calculation. Okay, so we considered this thing that you have you have a star of mass m, and you want to know, because of this attraction between these two, it's sort of trajectory of this guy is deflected by some angle. Right, so there is it has a velocity v. So for example, one approximation that I've done is I've actually assumed this m is at rest. You can do this very quantitatively reduced mass and all that, but the idea is not to do that. Okay, just to give you a sense of when you can ignore ignore these two-body interactions. So this is the sort of building block of these two-body interactions or collisions. Okay, and a lot of these concepts also apply to plasmas. So the gravitational problem is very similar to the problem of collisional interaction between within a plasma, because both these forces go like 1 over r squared forces, right? Unlike molecules, right? Molecules are neutral, and only when the molecules are very close, they interact strongly. Far away, the molecules are essentially do not know about each other. So this is a big difference. So we did this problem with an impact parameter b. If this is the impact parameter, this distance between the projectile and the test mass, we actually calculated, and the impulse approximation essentially says that this angle of deflection is small. Right, so basically even before the interaction and after the interaction, it's sort of essentially moving in a straight line. Delta theta is small. Right, so delta v perpendicular to the initial velocity is equal to 1 by mass times dt times f perp. All stars are of mass m. F perp is the velocity, the force perpendicular, the gravitational force perpendicular to the direction of motion. So that's just basically in impulse approximation, right? So f perp, okay, let me just write here. F perp is equal to gm squared by b squared plus x squared, 3 by 2 times b. X is this, distance from this closest approach. This is sort of an x, right? So, this is the force perpendicular to the direction of motion. So it's just gm squared by r squared times cosine of that angle. Okay, so this is equal to so g m by, so plugging in that f perp in this, you get dt by 1 plus Vt by B the whole square times 3 by 2. Right. So this is a simple integral to 2. If you do that, what you get is twice G. So this is for a fixed impact parameter B. So B is constant. So this is G M by B B B B, which is also the same as GM by B squared. This is all small m times twice B by V. So this is sort of like the if you want to concentrate all the force at an instant, this is like a force or the acceleration in the impulse approximation, and this is your the interaction time. Essentially, when the test particle is far away, they aren't interacting much because the force goes like 1 over r squared. Only for this time you have this strong interaction, and this can also be written as V escape squared by V, right? So V escape is the escape velocity from the particle, not from the galaxy, from the individual particle of mass m. So what it says is delta V perp will be substantial only if so delta V perp by V is sort of like V escape by V the whole square, right? So the particle will deviate substantially from its path only when the escape velocity is large or comparable to the velocity of the particle, escape velocity from the point mass. Okay. Okay, so I think we did this last time, and we also talked about this 90-degree scattering. Basically, when the test particle deflects substantially, that is delta V perp is of order V. When does that happen? When this is of order unity, right? And that would correspond to a given B, right? So there is a mapping between B and delta V perp. So 90-degree scattering happens when this guy, so twice G M by B V squared is of order unity. So B is just B90 is order twice G M by V squared. So what is the impact parameter necessary for the test particle to be deflected substantially? So if V is large, B90 is small, right? If the test particle is moving fast, you need to be very close in order for it to be deflected much. So it makes sense intuitively. Okay, now this is for a given impact parameter B, but in general you will have like a range of B's, right? So we have to find what will be the deflection if you have a randomly distributed B. So we are actually considering uniform distribution of stars and all that. It's an approximation because stars have the density in a galaxy and so on have profiles, some distributions, but we are actually giving you some qualitative ideas which sort of apply okay if the scale of variation of the density is larger than the scales at which we are interested. So what will be the number of encounters with impact parameter in range B to B plus dB? Number of encounters with impact parameter within this range if we have, say, n is the number of stars, each of which are small mass m, number of stars, and r is the size of this stellar system, say galaxy, the length scale of the galaxy. So number of encounters with impact parameter B to B plus dB in a single crossing. So basically, single crossing means you are covering a distance of 2r, the diameter. So this delta n is this number of encounters in a single crossing across the galaxy. So this is equal to total number of stars divided by the area of the galaxy. So this is the number per unit area of stars in the galaxy times the area covered by this impact parameter range, right? So typically, in a single crossing, you will have much less than 1. The delta n typical value would be much less than 1. In a single crossing, you won't have strong interaction even once. So this is just the ratio of the area of this annulus, right? With impact parameter b to b plus db, and this is the number of stars per unit area, right? So it's sort of like asking that you have this scattering centers, and if you throw some test particle randomly, what is the chance that they will collide? It's just the area that you're interested in, which is 2 pi b dB, divided by the area of the target times n is the number of stars, potential number of stars. So this is right. So this is the standard thing that we do when we do collisions. Okay. Now we also know that when you have a test particle moving, you will have some mass here. There is uniform distribution of matter. So sometimes you'll get deflected in this direction, sometimes you get deflected in that direction. If the system is isotropic, you should not have a net deflection. So that is delta theta can be positive, negative, and in general, the average of delta theta will be 0, right? After many collisions. Or average of delta v perp is 0. But this does not mean that there is no effect of collisions, right? What will happen due to these strong interactions is that you will have a random walk in theta. Although you will have a mean theta value which is 0, you will have spread of theta. Okay, so let's actually calculate summation over sigma delta v squared. So this delta v is delta v perp actually. The parallel velocity does not change to lowest order in this approximation. So delta v perp squared is equal to delta v. So I'll be using delta v perp and delta v interchangeably. It's the perturbation in velocity in the perpendicular direction times delta n. This delta n is this number of encounters with b to b plus dB. So this is the total RMS spread in velocity in a single crossing of the galaxy, right? So this is sort of like a random walk argument, right? So this is the number of steps, so to speak, in the random walk, and this is the square of the change. So it sort of goes like the RMS displacement or RMS change in velocity is proportional to square root of n rather than n itself, which is the ballistic regime. Okay, so if we plug in things, what do you get? So you have, so delta v perp was twice gm by, for a given b, b to b plus dv. This is your delta v perp squared times twice n by r squared. This is just this guy, right? I'm just canceling this pi times b dB. So this is the number of, this is change in RMS perpendicular velocity in a single crossing. Now let's sum over all the b's. So let's just call that delta v perp or delta v squared in a single crossing that would be, so now I'm actually integrating over all possible values of impact parameters B. That would be, so this integral sum B min to B max, the range in impact parameters, and you have so to 8 n g m by r b the whole squared times b db by b squared, right? You see, there is 1 by b squared here, and there is b db. Everything else is independent of b. That comes out of the integral. So what you have is 8 n gm by rv the whole squared times log of b max by b min. Okay. This is the 1 by b db integral that you have. This factor is called log lambda also, where lambda is called, this is called Coulomb logarithm. Coulomb factor in plasmas. I mean, it's exactly the same calculation in plasma because it's 1 by r squared force, the same thing. So that's why it's Coulomb, who worked on electrostatics problem. So, but it's identical. So that's the terminology. And so what should we, so you can actually see that the dependence on the value of these limits is pretty weak, right? It's even if you increase B max by a factor of 10 to the 3, this just changes by something original value plus 3. It's a logarithmic dependence, which is actually good. What it means is, you don't have to bother too much about B min and B max, but we should still want to know what B min and B max should be. And for that, we know that the impulse approximation breaks down when B is equal to B90. So we can actually choose B min is equal to B90. This is the small impact parameter for which deflection is substantial, which is equal to twice gm by v squared. It's nothing but, right, half v squared equals gm by b90. It's basically the potential energy is equal to kinetic energy. If I do that, this is what I get. So this is a good approximation for the lower limit of this. Okay. And a good approximation for B max would be R itself, right? I mean, the stellar system size is R, the integral should not integrate beyond R. So this lambda should really just be R by twice gm by v squared. But we know that in a gravitating system, velocities are determined by the depth of the potential well. So we know that, like, from virial theorem, for example, we know that half mv squared, is of order g m sorry, half m, the global virial theorem. So the m is total mass m by r. You can put a factor here. Okay, if it is an extended potential or whatever. The point is v squared is gm by r. Okay, so this is basically like what we use all the time, right? The circular velocity in a galaxy, or the velocity dispersion in an elliptical galaxy, satisfy this sort of a virial relationship. So if we plug that in there, what do we get for lambda? And this is nothing but g times n times small m by r, right? So if you plug that in, you can actually see this r cancels, this g m cancels. So lambda, so this implies lambda is like n, right? total number of stars in the system, essentially. So, so if you go back to this delta V expression, so delta V squared in a single crossing of the galaxy, we have it as right. So this we can actually just put. So this is, you can also see it from here. So we can actually eliminate a lot of things. So so this is 8n times g m by r squared times 1 by v squared. 1 by v squared is r by g n m times log n. Delta v squared in single scattering by v squared. So if you plug in everything, everything will cancel out, and what you will have is 8 by n. Right? Just remember, v squared is equal to this. This is the global velocity value in that gravitational system. 8 by n log n. This is a very important formula. What it says is that in a single crossing of a gravitational system, the stars will undergo delta V by V, which is of order given by this. So if n is large, if the stellar system is consisting of a lot of stars, individual stars, in single crossing, you just have very little deviation from its original path. So it does not really collide with essentially anything. It's actually somewhat counterintuitive. Larger n makes the system collision less. Normally for gases and so on, higher density would make you more collisional. Here, the velocity itself is determined self-consistently because of the depth of the potential well. Because of that, we get this non-intuitive answer. Right, so here, so this is delta V perp, which is given by 1 by V. So delta V by V squared is 1 by V squared. And that V squared increases if your n increases, right? For the same small m mass. So that is really the fundamental reason why the system is collision-less for a larger n. Okay. So we can actually answer another related question. What is number of crossings required to make delta V of order V, right? This is like if you throw a test particle at this stellar system, when does it forget its initial velocity, right? So the number of crossings required for this would be, so you just have to, so this is in a single crossing. So we know that this is a random walk process. We have already written this down, right? So this, the number of crossing required. So we want to put delta V. So we want to put V squared times 8 by n log n, right? So that's just delta V squared times the number of crossings is equal to unity. What I have said is delta V squared by V squared times. So this is the number of crossings required for this test particle to forget its initial conditions. So that would be, that's called n relax number. So this is also called relaxation. This collision process is also called relaxation. Two-body relaxation is the technical term. So n relax is equal to V squared by delta V squared. And if you plug that in, this is equal to This is just, this one would be just n relax, right? That would be n by 8 log n. Right, I think it's divided by v squared, which I had missed. Okay, so basically the number of crossings required goes like 8n by n by 8 log n. So you can actually ignore everything else, can actually be ignored. It's just proportional to n. Because like, suppose your n is 10 to the 11, right? This is 10 to the 11 divided by natural log of 10 to the 11, which is really nothing. So this is an important thing. So we can also define something called T relax, right? We can convert this number of crossings required for relaxation to a time required for relaxation. That's nothing but n relax times T cross, right? T cross is the crossing time across this system. That's nothing but, this is nothing but R by V. Right? That's the time required for it to cover the substantial part of the stellar system, and n relax is that. So in other words, T relax by T cross is equal to n by 8 log n. Or you can actually write as 0.1 n by log n. Now, this is very handy thing. So this tells you beforehand when do you have to worry about two body relaxation, when not. For example, like Milky Way galaxy has about 10 to the 10 stars, right? N is huge. The crossing time for Milky Way is sort of orbital time of the sun around the center of galaxy is around 200 million years. So T relax is 200 million times 10 to the 10. That's like humongous. I mean, essentially, a typical star of Milky Way remembers its trajectory from long time ago. It hasn't had time to interact with other stars to randomize its trajectory. Okay, so this is what it means through two-body interactions. There can be other like resonant interactions and so on. We are just talking about these collisions when two stars come close and get deflected substantially. That's what I'm talking about.
You're saying that that crossing time is R by V, so that means that the star that's fixed. So you're just saying two-body interaction.
No, this one, the T cross is a global crossing time. So how long does your typical star take to cross the gravitational system?
But wouldn't in that time period it will also experience scattering due to other fixed masses, right? Because you drew that diagram where V was randomized.
So yeah, that's what I actually calculated, right? It will do interactions, but most of them will be small angle interactions. It will not have the required number of collisions or interactions required for it to get deflected substantially from its initial location. So what I'm saying is not that it will totally have no, it would have totally no interaction with discrete stars. It will, but it will essentially be moving along an undeflected trajectory. It's not that like you will have no interactions. It will have, but it is more or less hasn't had large deflection. Okay. What is the value of V in astronomical which we can consider an value where there is a so let's see. Right. So. So, if you put in a solar mass, the B value would like turn out to be of order AUs if you plug in the numbers, astronomical units, which sort of makes sense because the nearby star has to come very close in order for it to have strong interaction with the sun. Okay. Normally the nearest star is a parsec away, which is like 10 to the 5 times the AU. So essentially, they won't have strong deflection, cause strong deflection. And for this case, for the solar case, here we should not put 220 kilometers per second. It's the relative velocity with the solar neighborhood stars, right? Because they're sort of essentially moving together. That would be about 10 kilometers per second. So if you want to calculate this, you put this as a solar mass, you put this as like few tens of kilometers per second, and then you calculate it. And my memory is that you get something like AU, 10 AU. Okay. Okay, so this is fine. This is an important concept, and it applies to plasmas as well. In case of a plasma, this lambda factor is the ratio of something called the Debye length to this B90. The equivalent it's just E squared by KT, right? In CGS units, E is the charge of an electron, E squared by KT. That's the nearest distance. But this lambda d is not the global size. In a plasma, there is something called Debye length. So if you put a charged particle in a plasma, the other charges will move and shield the presence of this test particle over a scale of order the Debye length. That's why you don't have to put in as R max as the size of the system, but lambda d. Whereas in a gravitating system, you don't have shielding. All masses affect your test particle, so your R max has to be the system size. Okay, but all this notation, all this carries through to electrostatic interaction between charges. Okay, so let's see. Let's put in some system. So say Milky Way. Let's say Milky Way has about 10 to the 11 stars. T cross I already mentioned is 200 mega years. So T relax from above, if you plug in this, is about 4 times 10 to the 6 times the Hubble time. So basically, over a Hubble time, stars, a typical star in Milky Way hasn't had strong two-body relaxation interactions with particles. Let's put in something else, globular clusters. So globular clusters have n of order 10 to the 5, 10 to the 7. T cross is basically the size of the core of the globular cluster divided by the sigma. Sigma is the velocity dispersion. Globular clusters are spherical systems. They don't have rotation, but they have this velocity dispersion. If you plug in the typical numbers, RC of order parsec, few parsec, sigma 10 kilometer per second, you get this as a million years, mega year. Okay, so let's see. So T relax, if you plug in these numbers in this formula, what you get is, let's see, 0.1 times 10 to the 5 by log of 10 to the 5 times mega year, which is the crossing time. So that comes out to be about a giga year. Right, so this is actually less than the Hubble time. So what it means is that the globular systems are old enough for the two-body relaxation processes, these collisions between. So this is what is called collisions, right? You won't have collisions as in molecules like the two stars will just come and blast against each other. Those are extremely rare. But you do have these deflections because the cross section of a star is tiny, right? 10 to the 11 centimeters is nothing compared to parsec. So that is extremely rare, but that also can happen. I mean, there are so many stars and so many galaxies out there that even a head-on collision between stars is not impossible, but it's extremely rare. So what does this mean? What it means is that over the lifetime of a globular cluster, you have to worry about relaxation. So what normally relaxation means is that different stars in globular clusters have had time to exchange energy, right? So in a collisionless system, uh, if you have a global potential, like the smooth potential of a galaxy, in a collisionless system, uh, whether you are a very massive star or a low mass star, you move with the same acceleration. Like Galilean, the great experiment of Galileo, whether you drop a feather or a cannonball, reach the ground at the same time. So that holds for a collisionless system, right? For a collisional system, like molecules, for example, if you consider uh, oxygen molecule and hydrogen molecule, H2 and O2, they are colliding with each other in the atmosphere. They share their energies. So their kinetic energy or their temperatures will become equal because of collisions, but not their velocities. So if the temperatures are equal, the typical random velocity of hydrogen will be much higher than the typical random velocity of an oxygen molecule. So that's sort of not like the uh, collision-less system where whether you are, so what this has profound impact on, say, globular clusters, which are collisional systems. So what this means is that suppose you have a range of masses of stars in a globular cluster, the the stars will try to make their mean kinetic energy equal. That is, their temperatures equal. The more massive stars and black holes and so on, uh, since their velocities have become less, since they have shared it with their low mass neighbors, they will actually sink to the bottom of the globular cluster. Whereas the low mass stars will have the same kinetic energy, but their mass is less. So the velocity dispersion are huge. So over their lifetimes, the globular clusters can actually evaporate. Most of the massive components of a globular cluster, like black holes and neutrons, all these massive guys, can actually sink to the center, and the low mass stars can just be kicked out. Okay, so this is uh, because of this collisional process. If it was not collisional, all of them would have same acceleration, same velocities. This segregation is not possible. It's exactly the same reason why the Earth-like planet would lose H2 from its atmosphere, but retain more massive molecules. Because they are collisional, they share, So this is actually a very profound thing. So for globular clusters, we have to actually worry about this mass segregation and all that. And if we assume that these are spherical isotropic systems, and we assume, let's say, they reach a Maxwell-Boltzmann distribution, right? So a perfect Maxwell-Boltzmann distribution has a tail. I mean, not quite a tail, but there are a number of stars which, let me actually just mention this. So say this is FV, the velocity distribution of stars. So this is 3D velocity, like speed. So you have, like in gas, right? So this velocity, let's say, is the escape velocity from the globular cluster. So you will have this portion of stars which will escape the globular cluster. Then because of collisions again, the distribution function will try to relax to a Maxwell-Boltzmann with the tail. So all these tail is populated because of collisions. And because of that, it's slowly evaporated. A globular cluster can evaporate over its lifetime. Okay, so this is an important concept that you should be aware of. Okay, what other? Feel free to stop and ask questions. So, say open clusters. What are open clusters? Open clusters are these young star-forming clusters like Pleiades and others, and they have much small number of stars, 300 stars, and their crossing times are shorter, say, actually not shorter. Their crossing times are of this amount. So their radii, their sizes are bigger than globular clusters. Globular clusters are very compact. Uh, Open clusters are diffuse; they are spread over much bigger, and their velocities, sigmas, are also smaller than the sigmas here. Okay, so what is their T relax? So T relax would be, if you plug in the numbers, so 0.1 times 300 by log of 300 times 10 megayears. So this is about 50 megayears. So they are, but remember, the open clusters have a very short lifetime. They are, I mean, their lifetimes are equal to the lifetime of the massive stars that they have. So they actually just go away over the same time scale. The lifetime of a B star, of a massive star, is about this much. Okay, whereas the globular clusters are made of very old stars, so they are essentially, the stellar evolution is not happening in globular clusters over their lifetimes, but here it is. But after this time scale, they should also forget their initial velocities. Okay, and you can do the same exercise for various things. So for open clusters, two-body relaxation is important. Say galaxies in a cluster, right? You can actually think of a galaxy cluster, which we'll encounter later, is a collection of a self-gravitating collection of galaxies. So if you have, there are about 1,000 galaxies in a cluster, so 10 to the 3. Okay, and the crossing times is about like a giga-year. 1/10 of a Hubble time is the crossing time of a galaxy within a galaxy cluster. So, so what is the relaxation time? So you can actually see the relaxation time is so 0.1 times, it's 100 by log of 100 times the crossing time. So this actually is less than their age, T Hubble. So galaxy clusters, oh, sorry, let's see. So 10 to the 3 times a giga. So in fact, I wrote it wrong. So galaxy clusters are also not perfectly relaxed bodies. So you can actually see preferred directions of galaxies and so on in galaxy clusters. And that's basically, that means that they haven't isotropized their orbits. Unlike in globular clusters, it almost is spherical looking, perfectly spherical, and the velocities are all random isotropic. Okay, so that's what happens when the system is collisional. The velocity distribution is isotropic, and if there are no other additional conserved quantities, they are the distribution function tries to go to Maxwell-Boltzmann, just like in a collisional gas. Yes.
So if there are smaller globular clusters, for example, in a galaxy, so we've seen that within the lifetime of the T Hubble in that scale, the individual stars in the galaxy will not get randomized the velocities, but within those small clusters, the velocities will get randomized.
Yes.
So like, are we forming small blobs within the galaxy which are still going in the initial velocities? Like, how does it actually look like?
Yes, in fact, Gaia has shown. So this Gaia is this ESA mission, which has actually measured the proper motions and the line of sight velocities of a lot of Milky Way stars. So what it actually has shown is there is like a group of stars which are extremely coherent. In fact, and they have identified, they have called them like by names of rivers. Like, oh, this is a, in fact, one of them is called Jhelum. This is the Jhelum stream of stars. So basically, you can actually see these things moving together in one direction and then crossing some other stream. And basically, what it means is that they know, like 10 giga-year ago, where they came from, some sort of a giant merger with some other galaxy, but the remnants of those motions are still there. If it were a relaxed system, we could not, like, none of that we could actually see. Okay, so you do see the evidence of this thing. Mm. Right. So the other thing is when we do n-body simulations, right? So doing a simulation with 10 to the 11 particles is actually hard. Even now, it's not possible. So early numerical simulations of say Milky Way tried to say, okay, 10 to the 6, stars we'll be using. But see, if you reduce n, you artificially make your system collisional. You will have artificial relaxation if you don't have enough star particles in your simulation. So what do? And this is exactly the same. The reason is exactly the same. You have these discrete things. Larger the n, more collision less you are. So what did people do? First, you actually increase n, right? So you try to increase n as much as you can, but if you cannot, the other sort of trick that people do is something called gravitational softening. Gravitational softening. So what gravitational softening does is instead of using a gravitational force which goes like 1 over r squared, you make it go as 1 over r squared at large radii, but then saturate it. So the gravitational force gets softened than the actual value that it would have been if it were a point particle. So this is called gravitational softening. And the way gravitational softening helps is through this Coulomb, this lambda factor, right? So instead of lambda being the system size to be 90, now it will be the system size to the softening length, right? Because you will not reach, your your gravitational force will not be as strong if you go closer in. It will be saturated at this 1 by rs squared kind of a value. So this is other trick that people use. So one is increasing your number of stars that you simulate. And this is actually a real issue. A lot of, like, if you look at n-body simulation literature, you will actually find a discussion of all this. So this is one trick that people do in order to, right? So there is this log lambda factor, right? So normally it's log n, but if you make your RS bigger, this can actually be reduced by some factors. Okay, so and this, we will actually deal with these in the form of softened profiles and so on. We'll actually come to that. Okay, so any question about the two body relaxation or collisions? It's an extremely important concept, because of this almost uh, negligible effect of two body relaxations. We can actually use density distributions like rho as a function of r to model galaxies. If these two body relaxation, if these two body processes were important, that approach would not work, right? In that approach, what you're saying is that the gravitational influence of masses which are far away is much more than the gravitational influence of masses which are very near you, right? So for example, it's not always true. For example, the solar system for the sun, of course, it's not an n-body system. It's like perfectly, you have to solve Newton's laws in order to do gravitational thing, gravitational problem of say solar system, right? So, but for galaxies, you can just use a smoothened, like for example, for the motion of the Earth, you cannot just smoothen sun and the planets and just get away with that, right? But for galaxies, you can. The problem with the open clusters is that they are not long lived. Open clusters are defined by the young stars. So you cannot really follow, you cannot notice them after the most massive stars are gone.
But for example, if you have say 1,000 stars in it's a typical open cluster, then can we observe this mass segregation?
I mean, as I said, you don't have old open clusters by almost by definition.
How old?
Like 100 million years or something. When you don't have massive stars in that.
Is the calculation only for disk galaxies or for any kind of galaxies?
These arguments are apply to this. The fact when should you have relaxation applies to all type of galaxies. For example, elliptical galaxies may appear spherical, but they are collisionless systems. They may appear, oh, they are like very spherical looking, but they're, if you look at their isoforms and so on, they are triaxial. They are extremely complicated orbits in there. They are not relaxed systems. So now we'll actually come to potential and stuff. So gravitational potential. So I mean, this we have all done a lot of times. I'm just gonna, give you the results essentially because you have done this. So if you have a bunch of particles, and if you want to calculate gravitational potential due to that, your coordinate system, and this is your, say, x, and so your phi x, of course, is minus summation over alpha gm alpha over x minus x alpha. And this stuff you have encountered all the time, so you can just, you don't have to bother at all. So this is the gravitational potential at point P due to these masses which are labeled by alpha. So you sum over all those and you get the gravitational potential. You can actually go to the continuum limit as well, and you can write your mass as you can use these tricks, right? We have done this 1 over 1 by x minus x alpha prime. Right, so this gives you this is the potential gradient of the potential, gives you the gravitational force per unit mass, and and then you have delta squared by x minus x, or x prime. So this is like a discrete limit. Now x prime is the continuum label that you use, and this is of course the delta function. Right, so this, we have all done this in electrostatics. This is done to death, so we won't really do any of this again. So this potential satisfies, if you do all these manipulations, it sort of satisfies this equation. Okay, that's got phi equals 4 pi g rho. This is the Poisson equation for gravitational potential phi. I mean, this looks like the electrostatics. This is equivalent to electrostatic equation for the electrostatic potential, and all the techniques that we learned there can be applied here, right? All the techniques like the separation of variables and the Legendre polynomials, YLMs, Fourier expansions, if you have periodic boundary conditions, all that just applies here. So we'll not actually do that because that's already done in great detail. Like Gauss's law, right? We are E dot ds is charged enclosed. This in the same way, you can actually do the gravitational acceleration dot ds is sort of mass enclosed. Is proportional. All this we all know, so we'll not go into this. But all the tools that we learned there can just right away apply in gravity. Okay. But we should start with something, we should do something classic which you already know. So Newton's theorems. Newton's theorems. So Newton actually had these two theorems in his book Principia. One is inside a sphere. So if you have a sphere, which is a spherical shell, right? Inside a spherical shell, there is no gravitational acceleration felt by a test particle. Okay, I mean this is a well-known thing. You've done it for in many ways. So if you consider any point here, and if you consider, say, so this is some general point. Okay, now what Newton sort of showed is that this force on this test particle from mass here and this force actually is equal and opposite. For all pairs, this can actually be shown because this solid angle is this. So let's just do this construction. So this solid angles are equal. So what is, and the mass in this sort of little conical region is delta m is equal to mass times this solid angle by 4 pi, right? This is the mass within this little cone here. Similarly, this one times, sorry, so this is mass by right, so this distance and this distance are not equal, right? It's a general point. So let me actually just so let's say this is the distance d1, this distance is d1, and this distance is d2. So so this is d1 squared so this is actually like this, right? So it's like sigma. Sigma is basically the mass. So it's a uniform density shell. Sigma is mass per unit area for that shell. So this is mass per unit area, and this is the area, right? This is the area of this little, like an infinitesimal part of this shell. Similarly, this one is delta omega. So delta omega is the same, right? We are taking just this cone extended on the two sides. So the solid angle is the same times d2 squared sigma. Let's see. Right, that is correct because this is mass per unit area. This is just the area. That's correct. So let's just get rid of that. And the force. So this is like dm. This is like a dm. So this mass is a little like if d1 is bigger, this mass is a little higher, but the force is gm by d squared. So if you just divide by this by distance squared, this is just that. And if you divide by d2 squared, this is just equal and opposite, right? So for any general point, the force on this opposite side of this cone is equal and opposite. So since they cancel in pairs, the whole sphere will contribute 0 acceleration to any point within the sphere. So what it means is the gravitational acceleration inside the spherically symmetric shell is 0, or the gravitational, the inner part of the shell is an equipotential. So potential everywhere inside is the same. So this is Newton's first theorem. Okay, Newton's second theorem is actually a little more subtle. And Newton's second theorem says that if you want to consider, so like say, if you want to calculate the potential here outside due to a distribution of mass, spherically symmetric distribution of mass inside this point, what you can actually do is so you want to calculate the potential here, you can actually replace this same mass and put it at the center, and then calculate the gravitational potential due to that. This is Newton's second theorem. Okay, so instead of having to calculate gm by r minus gdm by r and sum that up over this complicated surface, if the system is spherically symmetric, you can put all this mass at the center and just calculate minus gm by this distance. So it's actually a very useful thing, and apparently it took Newton 20 years to figure this out. 20 years to a person who invented calculus. It took him 20 years to figure out to give this an argument which was foolproof. Okay, so things which are trivial now, when things are discovered for the first time, they are actually quite tricky. So let's consider this point P, and let's just consider this center, and let's consider this. So this is point P. This is in the inner. So P prime. This point is P prime. Okay, and let's consider another situation, which is a point Q here and a point Q prime here. Okay, so the potential at point P due to mass at Q prime, right? So this mass is causing potential at this location, right? So what is that? That is just minus, and so so this is the place where we want to calculate potential. This is a shell of mass m, so this is minus g delta m q prime by pq prime, right? This is just the definition of the potential, minus gm by the distance, and this delta m q prime is equal to mass times delta omega by 4 pi. This is correct. So the mass in this particular part is nothing but the total mass of this shell times solid angle, this solid angle, this delta omega, and which we take equal to this solid angle. So this is just that. So this is the potential at P due to this little portion at Q prime. Similarly, what we can actually do is you can calculate the potential at P prime due to this mass here at Q. And we actually consider the same amount of mass spread over this bigger shell. So that's nothing but minus g delta m p prime by p prime q. But p prime q and pq prime are equal. These distances are equal by symmetry. So this guy is equal. So, and what about delta m p prime is equal to m times delta omega by 4 pi, because the same mass is spread over. So these two potentials, right? The potential at point P due to this little part is equal to the potential at point P prime due to this mass. Okay, and this can be applied to all such patches. Okay, so what it means is that the potential at point P is equal to the potential at point P prime. So potential at point P due to the mass in this shell is the same as potential at this point P prime due to the same mass spread over this bigger shell. Okay, and the potential due to the so but inside a sphere, inside this, we already saw that potential is constant. So phi at P prime is equal to phi. You can actually just calculate it at 0, right? As I said, that the potential due to this at point P prime is just this, and that's just minus gm by r, and if this is this r. Okay, so what it means is that the potential at point P, due to a spherically symmetric distribution inside it, is as if all that mass is concentrated at the center. So it's a subtle argument, but it works. So these are, these we always use all the time, but this is the way Newton did it. We normally do it using Gauss's law and all that. Okay, so these are very important for calculating potentials and things like that. So let's look at spherically symmetric mass distribution. So if you have a spherically symmetric mass distribution, how do you calculate the potential at some point P? For gravitational acceleration, we all know, right? The gravitational acceleration is proportional to the mass enclosed within that radius times some factors divided by r squared, right? But the same you cannot apply for potential. So what's the potential? So we'll use these two theorems to write down the expression. So phi at a distance r from the center of the symmetry of this mass distribution, this is equal to, it's composed of two terms. One is the potential due to right, so one is this one. Right, so this is using theorem 2. All the mass that's inside, you can as if put it as if it is at the center. It's using theorem 2 to write this. This is the contribution due to all the mass inside the inside radius r to the potential. And then you have minus 4 pi g r to infinity rho r prime dr prime. This is due to theorem 1. So if you are calculating potential due at this point due to mass, spherically symmetric mass which is outside, that's just the work done in order to bring mass from infinity to this point. That's just this mass divided by, so this is nothing but 4 pi rho r prime square dr prime divided by r prime, and then you integrate. Okay, so this is the inside contribution to the potential. This is the outside contribution to the potential. This is important, right? You cannot just apply, you cannot just leave it at that, right? Unlike for g, gravitational acceleration, it's only gm enclosed by r squared. Here you have this contribution that's important for the potential. Now, of course, if you do this, then of course you should get, if you do this differentiation, you will get, because there'll be two contributions, right? There will be minus gm by r squared. There will be minus g by r dm dr. That would be cancelled by this guy. That's why you need the second, term in the potential, right? If you just do ddr of this, that's not good enough. You'll have extra terms. Okay. Anyway, this is all very well known to all of you. Okay. So now we'll actually do some, some common potential. So in astronomy and astrophysics, especially in galaxy formation, you want to, there are these very popular potential density pairs, right? So let me just write down common potential density pairs. So like NFW density for the dark matter halo, you can actually write analytically the potential and density combination for that. So basically your potential has to satisfy. So a potential density pair is something that satisfies the Poisson equation and sort of approximates the density or the potential with something that's sort of realistic as compared to the very complicated thing that you're looking at. Okay, so for example, the point mass, you have density equals Q, or sorry, mass times delta R minus R naught. Right, so if you have a point mass at a point R naught, this is the density corresponds. So where delta is this 3D Dirac delta function, and the potential, of course, is this we all know. Okay, so then we can actually do something called Plummer sphere. Plummer sphere. So this is a spherical potential that's actually very commonly used to say model a globular cluster, and also in numerical. So I actually mentioned this gravitational softening. The potential that's used for gravitational softening is Plummer potential. So how does that look like? Let's see. So the density of a Plummer sphere looks like 3AP squared by 4 pi mass divided by R squared plus AP squared to 5 by 2. Let's see. So this is how the density of a Plummer sphere goes like. So AP is some scale parameter. Okay. So so for small radii, the density becomes constant, right? And R is small. For large radii, density goes like R to the minus 5. It sort of falls very steeply. That's why it has a finite mass. Right? If you integrate 4 pi R squared rho dr, it will give you m. Okay, so this is the total mass. What about phi Plummer? This is equal to minus gm by R squared plus AP squared. Actually, you can see the sign of softening, right? So if I plot a point mass potential, that just goes like this, it just blows up. Whereas this guy, as you make R equal to 0, it's sort of nicely, this is Plummer. So this is the softening thing, that the gravitational acceleration is not increasing so much as you go closer in. It also helps numerically because the velocities of test particles and stuff will not be so high towards the center, the numerical calculation can come to a halt. Even if you have in the whole cosmological volume a single particle which is moving really fast, you cannot take a time step in the numerical evolution which is longer than the dynamical time as this thing. So if you soften the potential, you prevent the formation of very fast particles that would just stall your numerical evolution. So Plummer sphere is very useful. So this is used for softening, numerical softening of gravitational force in numerical calculation. So at large R, it's like a point mass, at least in terms of the potential, right? And in terms of density too, the density falls really fast. In n-body sims. So n-body simulations are these gravitational evolution simulations that are popularly used for evolving galactic systems. Now the question is, how do you actually derive a pair of density and potential, right? For a given density, solving for phi is a little harder, right? You have to solve this differential equation. But if you specify phi, you can always calculate del squared and calculate rho. But that also has a problem because rho can actually come out to be negative. If you take a del squared of something which looks reasonable, sometimes you can get a negative rho. So the people have tried a bunch of different things, and these, for example, this is always positive, and the phi has the behavior which is reasonable. So you people have tried a bunch of these things and seen which ones are have desirable properties. So this is Plummer. So it's used for, say, things like globular clusters. This is historically where this Plummer sphere or a softened gravitational potential was used. What else? So you have a homogeneous sphere. A homogeneous sphere. This is like rho equals constant, rho naught for r less than r naught, and 0 for r greater than r naught, right? So it's like a constant density sphere. This you have also done. So this has a total mass is equal to 4 pi by 3 rho naught r naught cube, and it has a potential, again applying that formula where you consider the inner part and the outer part. This is actually equal to minus gm by r for r greater than r naught. Of course, if you're outside, the inner parts contribute as if you put all the mass at the center. This is what that is. And this is equal to minus twice pi g rho naught times a squared, or r naught squared minus r squared by 3 for r less than r naught. Right, so potential should be continuous, which you can actually see. So here, this is written in terms of m, this is written in terms of rho naught. So potential has to be continuous everywhere, and it satisfies the Poisson equation. What about gravitational acceleration for a homogeneous sphere? So g equals minus grad phi. That in this case would be right. So that's nothing but minus g m enclosed r by r squared. Right? This formula is always valid. So the m enclosed for r less than r naught is so 4 pi by 3 rho naught r cube by r squared r hat. Right? This is your, if you plug in the enclosed mass, this is what you get. So this gravitational acceleration is proportional to minus r. Right? So if you write down the equation of motion for a test particle, is equal to minus 4 pi g by 3 rho naught r. So this looks like a harmonic oscillator. If you don't have angular momentum, this equation is just the radial oscillations, and this is essentially a harmonic oscillator, except that this is valid even if your amplitude is large, right? Because this is an exact equation. Unlike sine theta, you approximate as theta for a small angle oscillation of a pendulum. Here, the exact equation is a linear harmonic equation. So So what's the time period of oscillation? So time period is just 2 pi by omega, and this is essentially omega squared, right? So this is the equation for, so if we plug that in, so right, so sometimes people define a dynamical time, T dynamical, as the time that it so for this problem, the dynamical time is defined as something, basically that's just T by 4. So essentially, what's the time it requires for this test particle to go from maximum amplitude to the center? So the full oscillation will be like this, so it's 1/4 of the time period. The other thing here is that the amplitude, the time period is independent of amplitude, right? If you put a test particle far away, the gravitational acceleration is large. G is proportional to R, so it is pulled fast. So the time period is the same. It's independent of the initial perturbation R. So this is the dynamical time. So T dynamical is equal to 3 pi. If you plug in the values, it's just 16 g pi. Sometimes this value is also used for general mass distributions, except as rho, which is a constant for a uniform sphere, it just is replaced by the average density, volume average density. Okay, this is just a convention. Right. So So for a point mass for a point mass potential, we know, like even if you have angular momentum, we know that the time period is only a function of energy. Time, like Kepler's laws, the time period is only a function of the semi-major axis, right? Which is nothing but a function of energy. It does not depend on angular momentum. It only depends. So for a point mass object, the time period of the orbit does not depend on the angular momentum. In the same way, this is also true for this homogeneous sphere. Okay, and there is a general family of potentials for which the time period is only dependent on energy and not on angular momentum. And those potentials are called isochrone potentials. Okay, in fact, I shared a paper today about isochrone potential. Why, so Henon, famous French dynamicist, sort of came up with this. So this paper that I shared talks about how he came up with this and why this is so useful in a lot of applications. So it's called, in dynamical system, you must have heard of Henon map as well. So like he was an astrophysicist interested in dynamics. Isochrone potential. The isochrone potential is a general potential which has this property whose orbits, whose time period does not depend on angular momentum but only on energy, just like the Kepler's orbits and the uniform sphere, uniform density sphere. So this is, the potential is actually given by minus g. It actually has a simple form. Anyway, we'll actually not go into the details of all these. Last one is something called singular isothermal sphere, or SIS. Right. So we know about dark matter and the flat rotation curves and all that. A singular isothermal sphere is a simple model which can actually give you a flat rotation curve. So the density distribution of a singular isothermal sphere is equal to rho naught r by r naught to -2. Okay. And you can actually see the mass enclosed, which is 4 pi r squared rho dr, is proportional to r in this case, 1 by r squared dr. As you go farther and farther out, there is more and more mass which is enclosed. That's why it's a good model for a dark matter halo. Okay. Okay, and the potential for this is given by 4 pi g r naught squared times rho naught log of r by r naught. You can actually see that the gravitational acceleration is just gradient of phi. That will give you 1 by r. So v squared by r equals g. A flat rotation curve corresponds to a g which goes like 1 over r. So that's why it's a good model for a dark matter halo, which gives rise to a flat rotation curve. And there is something, this circular velocity, of course, is defined as this, right? V circular squared by r is equal to gm enclosed by r squared. So in this case, Vc is equal to 4 pi g r naught squared rho naught. This is the singular isothermal sphere. It's actually used quite a bit for dark matter halo potentials. Now the last one is something called the NFW potential. Okay, I'll actually give a homework problem on this. So rho is proportional to 1 by r at small radii, and 1 by r cube at large, radii. And it also has an analytic potential, right? The strength of all these models is they are analytic density potential pairs. So you don't have to solve the Poisson equation numerically or something. So the potential NFW, actually the NFW form goes like rho is proportional to 1 over r to r plus rs squared, right? You can see at small r, this is 1 over r, at large r, it's 1 over r cubed. And the potential goes like 1 over r log 1 plus r by rs, something like this. Very simple manipulation. So that's why most of the modern use of analytic potentials, people just use NFW, even though it's not the correct thing. There is evidence for profiles varying from NFW, but it has a great property that it captures this thing, qualitatively, and you can do calculations fast. Okay, that's why it's very, very popular. And the dark matter distributions in numerical simulations are actually close to this kind of a profile. So with this, we'll actually end today's class, and next time we'll start with flattened systems, right? Where potential is not a function of small r, it's a function of r and z or r and theta. It's a 2D potential density, and that's necessary for a Milky Way disk, right? Things are not only a function of spherical radius, but also on how far up from the disk you are, and things like that. So those are flattened systems. We'll start with that next time.